and welcome to this week's eBPF and Cilium office hours, also known as eCHO. This is episode number 190. I'm Liz Rice, and I am presenting this episode solo today. So I hope there are some people watching live who are going to catch when I make mistakes and correct me and just help me out through this solo episode. So I'm going to be looking at an implementation of the Enigma machine in eBPF. But before I get to that, I've got a couple of, let's say, news items that I want to mention. The first is I want to say a big hello to all my new friends from South America who I met at KCD in Lima in Peru a couple of weeks ago now, I guess. I also particularly want to introduce my lovely new Peruvian, well, Perubi is her name. Hi, and thank you so much to Enzo and Nelson. She's amazing. So Perubi is going to watch over me. Hopefully there's some other people out there also watching live. Do say hello if you are online right now. I guess one of the reasons why I'm presenting this solo is I know it's a public holiday in some places, particularly Switzerland, and Andre, who's the author of the Enigma Machine, is out on a public holiday today. So I don't know if that's widespread in other countries as well today, but hopefully there are some people out there watching. And if you're watching later, that's also great too. The other real big news for this week is that Cilium release 1.18 came out 3 days ago. In fact, this is Andre, who wrote the Enigma Machine, also did the release for this release of Cilium and many others in the past too. Absolutely loads of work went into this release. As you can see, we've got almost 1,000 people contributing to the project. So yeah, if you're thinking about contributing, you could be contributor number 1,000, which would be amazing. 3,000, almost 3,300 new commits going into this release. So there's an awful lot of really great changes going in. I'm not going to go through all the details this week. I think next week, or certainly in the near future, we will have eCHO episodes dedicated to looking at some of these great new features and improvements. But as you can see, there is an extensive list of changes, and including some day 2 improvements like performance and operations changes. So give that a whirl. Let us know how you get on. And yeah, as I say, maybe you will be contributor number 1,000 if you get involved. Okay, we've also had since the last release a lot of new case studies. If you're a Cilium user or an eBPF user, get in touch. We love to write up these stories about eBPF and Cilium being used in the real world. We've got the upcoming Atlanta KubeCon. November might feel like a long way away, but there will be CiliumCon there, as well as the full KubeCon and Cloud Native Con. So let us know if you're going to be at that. And the other thing I want to mention is that Cilium now has SIG community. So that's a group of people specifically looking at how we can keep growing the contributor base, keep growing people through their responsibilities up the community ladder, and also work on things like helping people adopt Cilium and get their stories out into the real world. Okay, wonderful. I think that's all of the new. Oh, look at the pictures of contributors here. That's great. All right. I think that's everything from the news point of view. So let's turn our thoughts to an Enigma machine in eBPF. So just over a month ago was Alan Turing's, well, would have been his 113th birthday. And Andre decided to celebrate that by implementing the Enigma machine in eBPF. And you might remember, or you might be aware, we've done some work in the past looking at how eBPF can be Turing complete, essentially by chaining together multiple eBPF programs. So although one eBPF program has a verifier limit of 1 million instructions, the ability to chain eBPF programs together and trigger them either by a timer or by messages being received means we can essentially implement anything, because we can make eBPF programs Turing complete. And so Andre decided to take as a challenge writing the Enigma machine, and also, as you'll see, the bomb, which was used to break the Enigma code. I'm going to guess most people have heard of the Enigma machine, but it was an encryption machine used during World War II by Nazi Germany. They were encrypting their messages, and Alan Turing and the Allied forces were able to essentially break that code, and the bomb was used to identify the setup for the way the Enigma machine is set up. I'm going to find, I've got a Wikipedia page open here as well, really just to show, let me make myself a bit smaller here. There we go. Really just to show what an Enigma machine looks like. And in particular, it's got these 3 rotors. So the idea is that an operator presses a key on the keyboard that creates an electrical signal that passes through the rotors. And as we'll see, the rotors kind of scramble that letter and determine what the output letter should be. So if I press A on the keyboard, maybe Q is going to light up. But then the rotors also move on, and that scrambles the letters, scrambles the coding for the next letter. So if I type another A, it might light up as, I don't know, Z the next time. So in order to understand the message, you have to understand how those rotors were set up initially, and also how they rotate as you type messages into the keyboard. Okay, so let's go back to the blog post. And I'm going to skip over, there's some really good writing here from Andre about dealing with the verifier, but I'm going to skip over that and move straight on to the bit where we talk about implementing the eBPF machine, the Enigma machine in eBPF. So I guess here the first part we can be aware of is those rotor positions are implemented as maps. And there's also this concept of a reflector. So my understanding of this is that the signal from the key goes through the rotors to the reflector, back through the rotors again, and we get the output character. So we can see here that implemented in eBPF, obviously there's something going on behind this process rotor macro, but we essentially take a character, forward pass it through the rotors, go through the reflector, backwards pass through the inverse rotors. And then, as I say, every time you hit a key, the rotors need to rotate, and that's what this step rotors part of the eBPF code does. So I think at this point, maybe it's time to not just look at some code, but perhaps we should run it. Oh, wrong screen. Here we go. All right, so this is the Enigma program. We just saw in the blog post here the maps, the reflector, the rotor maps and the reflector map. And yeah, code to step the rotors. And the other interesting thing is, how are we going to pass these messages through the machine? Well, the way Andre's done it is using UDP. So what we're going to do is send a message that we want to encrypt in a UDP packet, and an eBPF program attached to, well, the TC attachment point in the kernel. It's going to get that packet, and assuming that it is a valid packet, it's going to process that, process the contents of that packet. You can see here BPF loop. So we're really going to go through the payload of that UDP packet, one character at a time, and process each character. I also want to show you the make file here. Well, I'm going to show you the README too, because that's probably helpful. So this is the README on the GitHub repo. I'm going to skip over the animation demonstrations and just talk a bit about what you need to do if you want to run this. So there's a make file that Andre's provided that actually makes it really easy to set things up. And the first thing that we need to do is set up a network. Actually, I think maybe it's easier if I show in the README first. So in order to send or to have someone to send the UDP message to, Andre set up a namespace, a separate namespace that can receive messages. So we're going to send UDP packets from the host to the test namespace, and by hooking into the TC stack, we can what we're going to see is an encrypted message. So let's set that up. And as I say, there's a makefile that makes this easy to do. So we can see here, we're going to add a network namespace. We're going to add virtual Ethernet connection and address in that namespace. And well, so we've got a virtual Ethernet connection between the host and the test namespace. So let's get set up network. Okay. And at this point, if I do, I don't think I need to resudo over this, list the namespaces of type net. We've got two of them. One of them is the kind of the host namespace, and then also there's this test namespace. We can also have a look to see what BPF programs are currently installed, and I hope there aren't any. Let's have a look. Well, there will be some set up by systemd for control groups, but let's have a look. Log list. Yeah, all of these have been set up by systemd. Okay, so that's kind of a clean system. We'll also just check whether there are any maps. Okay, these are all related to running BPF tool as I was running BPF tool. Okay. So the README tells us, well, we've set up the network. I've already built, let's just do it just to make sure nothing has changed. Yeah, nothing to be done for build. And make install, this is kind of interesting. So make install, where's the install? So this is where we're going to add the Enigma eBPF program to the TC eBPF hook. Okay. It's actually also going to add the bomb. We'll come to that later though. So make install. Okay, so now let's have a look at the BPF programs. And now we've got some new ones. We've got this TC Enigma and TC bomb that have been installed and attached into the think if I look at net, we should be able to see where they are. Okay, we've just got the Enigma one installed, right? Okay. I'm going to say I'm a little bit surprised. Oh, it's probably because of it, the bomb might be in the other namespace. I'm speculating that. Okay, so what else do we need to do? We've installed the BPF programs. We need to pin the BPF maps so they can be accessed from user space. So where is that in here? That is pin the BPF maps. So there are lots of BPF maps. We ultimately want them to end up in sysfs BPF. I think it's TC Global. So let's have a look. Yes. So some of them already exist here. We're going to pin them to make sure they have the file handles that a user space program can access. Let's to make pin maps. Okay, and I think now if we have a look, yeah, we can see all the bomb maps are also in that directory now as well. We need to set up the rotor and reflector maps. So this is going to configure them with their default initial settings. Let's have a look at that. Setup maps, where's that? Set up rotors and set up reflector. So set up rotors, updates, does this update rotor script. This is, if I remember correctly, this is quite a complicated script, but you can, just by scanning it, you can see if this is doing things like applying ring settings, figuring out what the inverse character is, that what one character represents when it's been inverted. Okay. I didn't run that yet, did I? So let's do that. Make setup maps. Okay, so we can see the rotor and its inverse. So you can convert a character from, I think my example, I said A to Q. When you go in the inverse direction, you want Q to map to A. Okay. And we need to start with, both the sender and receiver have to start with a known rotor position. So let's do that. Oops, make reset rotors. Okay, so the BPF maps now have sort of 0 values for all of the rotors. Okay, now we need to have a listener. So this is going to be, this is basically saying run in the test NS namespace. We're going to run netcat listening for on port 1912 for UDP traffic. So I'll just copy that and put that into another terminal. Okay, so that should be just listening. And then we can do something like this. And we should see the encrypted version appearing in the other terminal window. And there it is. And if I reset the rotors again, and we take, you can see this QQDPF is exactly the same as in the README, so I can just copy this. And we should see it appearing as hello world in the receiver side. Okay, good. I actually wrote myself a little script that, well, it does make send message, and I added a little thing here just to save typing in echo my message and running netcat to send that as a UDP message. So I think I should be able to do something like hello echo, and that's been encrypted correctly. You might have noticed there were you might have noticed that it's turned it all into uppercase. That's because the rotors have 26 positions, 1 per character. We just convert everything to uppercase. If we were going to have lowercase as well, we'd need twice as many rotor positions. So we won't. There's no need to bother with that. Okay, so what else do we need to look at? We need to look at the BOM part. So the BOM is the idea that there's every day the sender and receiver needs to set their rotors to a known position. And if you don't know what the position is, everything looks like gibberish. You need to have the rotors set to the same position. But they used a common word or a common phrase. My understanding is, I don't know if they used exactly the same phrase every day, but they might, for example, have sent the weather forecast and used that as a way of establishing what the rotor settings were. And someone, I don't know if it was Turing, I have a suspicion it was someone else, but someone figured out that these common words were being sent every day, and that they could essentially brute force work out what the rotor positions were by looking for that common phrase. And I wonder if it's going to be here, we have a common phrase that we're going to use which is eBPF rock. There we go. So I'm going to have another window just running trace log. So this is going to output tracing from these eBPF programs. And if I send something that says eBPF rocks, yeah, the BOM is looking for, is brute forcing this known phrase, and having figured it out, it knows what to set the positions to. So I believe, let's just check what we do with the README. Yeah, so now we can set the rotor position to whatever this told us to set it to. Input equals this, and hopefully we'll get to see our unencrypted version. Well, there we go. eBPF rocks. Okay, so that seems to have worked. I guess one thing I wanted to do is show you that we can send messages just in the clear and then add the BPF programs. I'm going to see whether this works. I'm going to uninstall the eBPF programs. Okay, so let's just take a look at whether we've now, yeah, so we've got no BPF programs attached to the TC stack anymore, but I can still send messages and they should just appear in the clear. Episode 190. Yeah. So we're just using that eBPF program hooked into TC to do the encryption. And if we remove those eBPF programs, then, well, the traffic just gets sent in the clear as usual. Okay. There's also some really nice cleanup because Andre's, I don't know, done a really thorough job here and made it really easy to set this up and also to uninstall it. So we can do things like clean network and clean maps to remove the network namespace, to remove those BPF maps. So that's all really nice, I think. Let's just take a little bit more of a look at the code. So I got as far as showing you there's this BPF loop. Maybe that's worth digging into a little tiny bit more. So there is nice documentation on eBPF.io of lots of helper functions, but let's take a quick look at BPF loop. And what this says is we're going to call a callback function however many times we want to run the loop, and we're going to pass it some contextual information. So here we go. The first parameter is the number of loops. We pass in a callback function. We pass the context that we're going to use in the loop. So here we go. The payload len, that's the number of characters in the payload. We're going to call this Enigma process char function and pass it. Well, the context here is the, well, no, it's here. So it's the socket buffer. It also includes the length and the offset into the buffer, so the point that we've processed to so far. And what does this process char do? So it makes sure that we're not going to run over the end of the payload. It steps the rotors. I think that's what we looked at before. And then it's looking up the position of each of those rotors after they've been stepped. It finds the next character that needs to be encrypted from the payload. So we can see it there. It's got the SK buffer. It's going to look at the character that's, well, I characters on from the start of the payload in that buffer. It's only going to read one character. Now it gives us the character, and then we're going to do encrypting that character based on those 3 rotor positions. And then when we get the character back, or the encrypted character, we store that in the same place in the buffer where it was. So we were essentially taking that UDP packet and replacing each character as we step through the packet, encoding each character one at a time. Okay, well, to me, I think that looks like we've covered the intro. Should we have a quick look at the bottom code as well? Yeah, we could. Why not? So this is going to use another loop where we know we're looking for this eBPF rock text, and okay, so we've got, in this case, rather than sort of real rotors, this is a kind of we're going to test through all the possible rotor positions until we find a match or prove that there isn't a match. So, for example, if we were looking for eBPF rock and we don't find an E, there's no point going on looking for the B or the P. Okay. So looks like what this is going to do is it encrypts the crib and then it looks within the payload for to see whether it's matching. If it does match, then it knows what rotor settings to tell us. And if it doesn't work, continue the loop. So we have this the BPF loop function here, which is going to say the maximum number of iterations is 26 possible rotor positions for each of 3 rotors. So this is really brute forcing through all of the possible combinations of rotors, looking for that eBPF rock crib. Okay, so I think I want to just go back to the README, point out that there is some ASCII Cinema. Let's see if we can run this. I don't know how well this will work on YouTube. Let's find out. So this is the pre-recorded version of running what I just showed you. And it encrypted, we reset the rotors, and we can take that encrypted version and get back the original text. Okay. So everyone out there seems very, very quiet. So, but if you do have any questions or comments, then now would be a really great time to type them in. I'm going to point out here is the repo for that code. So AANM is Andre's, his username on GitHub, and you'll find it under Enigma. That's all public. Definitely encourage you to try that out. And you can also read more background on this blog post on the Isovalent blog that covers the background and some of the things that Andre was experimenting with as he worked through this really nice project. I think it's really, really fun project. So with that, I hope that's been an interesting sort of walkthrough of the Enigma machine in eBPF. It goes to show that we can really implement pretty much anything these days with eBPF being Turing complete. And I will wish you a wonderful weekend and see you soon.